Good afternoon. I hope everybody enjoyed their lunch, as I definitely did. So today I'll be talking about features that are upcoming in Lustre 2.9 or later. As you can imagine, this is not a roadmap that's set in stone. Obviously we'll do our best. There's a number of different organizations working on the features, and I'll mostly focus on the ones that Intel is developing. I'd put in the features from 2.8, but I know Chris covered them a little bit already, and so I won't really talk about those ones. The more interesting ones is what's coming up in Lustre 2.9. So there's the UID and GID mapping, which is a feature that's under development by Indiana University, and that one is been underway for a while, and it's my guess is almost certainly it'll be ready for 2.9. There's ZFS enhancements that Intel and Lawrence Livermore National Labs are working on. Project quotas from DDN. Shared key crypto, that's another project from Indiana that's hasn't been quite as active as the UID mapping, but individually and together those two features are quite interesting for WAN usage, but also they can provide some functionality for subdividing Lustre, a single file system, into multiple tenant kind of configurations. Progressive file layouts, I'll actually be spending quite a bit of time discussing that one, and data on MDT. So ZFS enhancements. There's a few different things that are underway here. ZFS was added in Lustre 2.4, and has been going along. There's an increasing amount of interest out in the community with people running ZFS, and as part of that, there's an increased focus. I mean, obviously, ZFS is relatively new compared to LDiskFS, and so the initial focus was on functionality and integration, and now there's enough enough interest in it to start focusing more on performance. And this is work that's was done over many years, working with Lustre and LDiskFS to improve performance in Lustre specific workloads, and the same is being done now for ZFS. 1 megabyte block size is something that has shown to be definitely a good performance for streaming I/O workloads. Is a big boost there, and so Livermore has integrated that into the upstream ZFS on Linux. There's some read I/O optimizations in the Lustre, the OSD side, and Alex, who's giving a talk later on ZIL support, which is good for synchronous I/O workloads. Which is, you think synchronous I/O, obviously you're doing lots of F-syncs, but also the case for multiple writers to the same file. If you have interleaved writers on a single file, then the OST will actually sync the file data to disk before allowing another client to access that data, to ensure that if those clients crash, the data is still consistent on disk. And so that actually generates quite a bit of sync workload, and Alex will be describing that one. There's also work underway that are changes to the core ZFS code. The first set were specific to Lustre OSD work, but for changes to the core ZFS, there's improved inode quota accounting, which isn't something that was in the original ZFS functionality. They only had block accounting and assumed that, because inodes are dynamically allocated in ZFS, you would just be, create a lot of inodes, it would come out of your space accounting. But there's, for administrative reasons and just, observability of how the file system is used, there's a desire to have inode quota. And so that's something, there's patches existing for that are, being pushed upstream into ZFS on Linux. Large D nodes, it's work that was done originally for LDiskFS many years ago, and it definitely improved the performance for handling small extended attributes. And again, Livermore has done the work to implement large D nodes for ZFS, and we're hoping that there'll be a similar improvement for handling Lustre extended attributes with the ZFS MDS. In the longer term, there's work underway to develop parity declustering and distributed hot spares or hot space for ZFS. And so this is modifications to the underlying RAID Z implementation that will allow you to optimize rebuild speed for RAID Z pools. If one of your disks dies, you can use not just a single hot spare worth of bandwidth to rebuild your pool, but use all of the drives, and they'll each contribute a small fraction of their space towards the bandwidth of rebuilding the drive of a failed drive in a pool. Moving on, there's also a variety of smaller features, or bigger features depending. If you're looking at the lines of code, if you saw Chris's presentation today, Oak Ridge has become a major contributor in terms of lines of code, and a lot of that is due to James Simmons. He's doing a lot of work. So that's Oak Ridge. But Oak Ridge and Cray, they're cleaning up a lot of the code and spending a lot of time that's really needed in a code base that's as old as Lustre. It's been around 15 years. And when it was first developed, Lustre 1.0 was on a 2.4 kernel, and it's come a long way since then. So cleaning up a lot of the code, keeping our master branch in sync with the upstream kernel, because as Chris said, there's some amount of fixes from major kernel developers, but the majority of the fixes coming from third parties are here's a patch to remove one extra space, and so there's a lot of time and effort needed to keep those in sync. And it does clean up the code and makes it easier to read, but there's other things that are needed in terms of restructuring the code and just cleaning up warts that have grown, and so there's a lot that's being done, and it's important things to do. DDN is also working on project quotas, and the work up until now has been in terms of getting the project quota feature into the upstream ext4 code base. And so this is something that will allow tracking space usage. It's almost like directory quotas in terms of there's a project ID. It's like a UID or a GID, but it's an independent identifier for a set of files, and it's inherited for new files inside a directory and subdirectory. And so it seems like it's a directory quota, but in fact you can assign a project ID to multiple trees in your file system. But it's a way to do space accounting and enforcement that's not tied to your permission model. And so that allows multiple, let's say you have a pool that's graduate students or whatever, they can be held under this one project, but they don't necessarily have to have access to each other's files, which is typically, people would add a group ID for that, but something you don't want to necessarily conflate file access with people working on the same project. And so that's the ext4 side of that is largely finished, and there'll be ongoing work to integrate that in the Lustre side. And another interesting area that's upcoming is network authentication and encryption. And so there's work for the 2.8 release to improve the Kerberos code, which has been in Lustre for quite a while, but sort of the unloved child. But Bull and Indiana, or actually Bull and Seagate, have been working on the Kerberos side. Indiana reluctantly got involved because they're working on a different encryption mechanism, shared key crypto, and they ran up against a number of old bits of code related to the underlying GSS API that both the Indiana project and the Kerberos code are sharing, and as a result, they also worked in reviving Kerberos, and so that's largely complete, I believe, in the 2.8 release. I think it'll be an ongoing project to make sure, because it hasn't been used very much yet. So, but it's something that's increasingly important and useful. And so this is, just to be clear, it's a network authentication. This isn't related to on-disk encryption or anything like that. But this is definitely of interest to many users. The other area that is moving along a bit slowly at this point, but data on MDT, and it's a method to improve the small file performance. And the idea here is rather than having the overhead of creating a small file with an inode on the MDT and then a separate object on the OST and storing your data on the OST, it's better to store a small amount of file data on the MDT. And that has several advantages, which is you avoid multiple network round trips for the data I/O and the locking of the object. Disk seeking on the OSTs. You might be contending with some big streaming I/O workload. Because the MDT is already optimized for IOPS, it's RAID 10 and maybe Flash these days. It can handle relatively small I/O workloads efficiently compared to the OST. It's RAID 5 or RAID 6. You store a 32K file, and the OST has a 1 megabyte RAID strike width. You're going to have a relatively high I/O overhead, even if you're discounting the RPC overhead to get there. So there's prototype code for this that we're starting to get to, and in the testing, do I have a graph? No, I don't have the graph in this slide deck, but we're seeing at least about two times performance improvement just on a simple benchmark with single disk MDT versus OST, right? And so that's the 2 times is about just the network performance overhead. It doesn't, we haven't done testing with RAID 6 versus SSDs and RAID 10 on the MDT. And if you start comparing with also an I/O workload concurrently, the streaming I/O workload on the OSTs, I think we'll get ahead of that 2 times. It makes up a small file, that's something that's configurable by the administrator and by the user, and This also works in well with the DNE2 stripe directories. You can, stripe a directory across multiple MDTs, and then if you're creating small files in there, you can get, multiple MDTs worth of disk bandwidth and network bandwidth for handling the small files. Because otherwise, without the DNE2, you'd be suddenly bottlenecked on one MDT worth of I/O performance as well. So just a little bit diving in here, with as you can see on the right, the data on MDT implementation, is avoiding, these extra RPCs. You don't have to do, lock and queue. You don't have to do a separate write to object create. In the initial implementations that we're at now, you still have to do like a separate, if you're reading a data on MDT object, you still have to do a separate RPC, to open the file, and then you do a second RPC to read the data. As it goes forward, just like Lustre, when you open a file, it fetches the file attributes and fetches, extended attributes back with a single RPC. We could also, if it's a small enough file size, if you don't have a big, we have already pre-allocated buffers on the MDS to receive, a 32K file layout, but of course it's a small file on the MDT, it doesn't have a layout. And so you can receive 32K in the reply buffer right off the bat, so you could reduce the number of RPCs even further, but we haven't gotten quite that far. There's URLs at the bottom for describing the design and things like that, and if you're digging into this, there's also a presentation on this at I think at one of the previous LUG 2014. The more interesting thing that's coming up is a project called Progressive File Layouts that we're working on with Oak Ridge National Lab, and it's really part of a bigger project related to layout enhancement. So currently today Lustre only supports RAID 0 striped files, and so that's fine, for the throughput area. What the project Progressive File Layouts is implementing is the infrastructure for these composite layouts, which is essentially a mechanism to have multiple types of layouts within one file, right? And so you can take, your current RAID 0 striped file and go to have, different parameters, striping parameters for different ranges of your file. The composite layout itself, has a relatively flexible structure. It's essentially a series of, there's a header, and you can have a bunch of components, and what's in those components is, whatever other type of layouts that Lustre understands. There's not, at the component level, there's no restrictions on what's in there except that they can't be, we don't support nested components. So what's in the components is, what's in the composite layout is a component, which is one specific layout that might describe a range of a file. Let's say, 0 to 32 megabytes, and you have a single striped file for the 0 to 32 megabytes. And then from 32 megabytes to a gigabyte, you might have a 4-striped file. And then after a gigabyte, it might go to, 64 stripes up to, 32 gigabytes. And then after that, you have a 256 stripe file. And you can actually have, there's up to 500 separate layouts within one file. The size is actually restricted by the total size of the extended attribute. What can you do with these things? So the project that we're working on now, that's progressive file layouts. It's essentially trying to mitigate the performance differences between small files with a few stripes and large files with a large number of stripes. And you know, handle this in an automated way so that users don't have to specify the striping themselves. That's one of the big user complaints is, you know, I didn't know my file was going to be big, or I didn't know how many clients were going to be writing to it. And so progressive file layouts is targeted specifically at that. But composite layouts themselves are actually a lot more flexible than just progressive file layouts. They'll provide the infrastructure for file level replication, right? So composite layout, you may have, actually I think I'll show that in a minute. Yeah, so progressive file layouts, you have disjoint sections of the file, each has a component. With file replication, you could have, you know, multiple components that are covering the same part of the file, and then you have two copies of the file, right? And so, you know, you keep those two copies in sync. It's like a mirror, right? But what happens if you don't keep the copies in sync? Well, then if one copy is old, you could have a file version, right? This is today's version, this is yesterday's version of the file, right? Or last week or last month. And so those files, I mean, it would still appear to be one file, and if you're reading from it, you'd read from the most recent version, but you could do an LFS, you know, give me this older version of the file, or you could do an ioctl on the file, and suddenly your file handle would revert to, this is the last week version, and you want to get the old version of your data back. The other area that's quite interesting is, we were talking this morning about HSM. One of the things you could do with the composite layouts is to have, you know, one of your layouts be part of Lustre, but the whole file layout is also in the archive, the file archive. And so then you could say, you know, if this file is released, you can actually, is it too low? I see people bobbing around. I'll lift my computer up, I mean, that'll help. No, you can restore potentially parts, you know, some parts of a file. If it's a terabyte file, you don't want to wait for it, you know, to come back from tape, and maybe it's so big it takes more than one tape. You don't want to have to wait for the whole thing to restore, so you could actually just restore parts of the file that are being actively used. So, and to be clear, you know, we're not working on all of these parts, but the infrastructure of composite layouts gives you the flexibility to do some of these functionalities in the future. So a bit more about what progressive layouts are. You know, have high bandwidth for large files. Have, oh, my slide didn't render properly. Oh, yeah, there it goes. So you can have, you know, low overhead for a small file. It only has one stripe, so when you're getting the file size, you only have to stat one object. You know, as the file grows, you get, you know, some more stripes. As it grows very large, you may have, you know, dozens or hundreds of stripes for the large part of the file. And, you know, you could do some of this stuff with setting static, you know, default striping on a directory. But if you, let's say you had a bimodal size distribution within one directory, you know, let's say at CERN or something like that, if they have, you know, a giant data file and then a small metadata file in the same directory, you can't specify one striping that's good for both of those files, right? And so this way you can have, you know, the small file threshold, you know, for the component 0 part, you set the size threshold big enough so that the metadata file fits on a single stripe, and then the big file, you know, gets most of the stripes. It also helps, you know, your space balance. You don't get the call in the middle of the night that one OST is completely full because some guy, restored his tar file and it's on just one OST. And it's worthwhile mentioning, so for the parts of the file that are covered up by another object, these ones are actually sparse. So they're actually, each of these components, to a large extent, appears like a whole file by itself. And the parts that are covered up are sparse. And so when you're building up these files, you can you build them using regular tools and join them together, or Lustre clients, they can just treat them like regular files, and during the I/O phase, they just index into a given component by the offset. And you don't have to do things like shifting data around depending on, which component it is. It's meant to be relatively easy to develop. So a little bit of, so we had done a prototype with Oak Ridge at the beginning of this year, and some performance numbers we got. So the main things to take out of this is that, with the PFL small, so consider PFL small, medium, and large to be essentially the same file as it's growing in size, and where you stop depends on how you're using that file. But the important thing to see is that if you have a single client writing to a relatively small file, you're getting about the same bandwidth. But if you were to have picked, this is you can't see it very well on the screen, but this is stripe equal to -1. So this is a fully wide striped file. This is the stripe equal to 1, which is single stripe. And so you get about the same performance for the small file. It's only a single client writing to it. But if you see here the stripe -1, if you're doing metadata operations on it, you got a lot of overhead, right, from having all of those stripes. But if you just have a small file, you don't need all of those stripes. You're only using the first one anyways. And conversely here, if your file is getting very large, right, you can see you're getting essentially the same performance as a fully widely striped file. And so you're getting the benefits of using all of your OSTs. And conversely, this is the bandwidth for the single stripe client. This is when a whole bunch of clients, and a bunch of threads on each client are writing to a single file, right? And so you're really getting, all the benefits of scaling without all of the overhead for the cases where you don't want it. And this is showing, parallel metadata operations. It says, for clients, many clients accessing these smaller files, you're getting, as you'd expect, lower overhead from, if each client were creating their own small file, right? So you get a high stat rate. Of course, the PFL large, you have more overhead, there's more stripes, but it's not really any worse than if you had optimized and created each file individually, right? So it's a pretty good improvement. I think it'll be a big hit with users. The other area that, there's no version up here, unfortunately, but this is something I think will be the next logical extension from the PFL project when it's done, is the file replication. And I think that this is something that Lustre really needs to avoid out of the... Okay, so file replication, I think, is something we need to do just to improve the reliability of Lustre. We don't have not depending on the redundancy of the hardware and failover. File replication will allow faster recovery from OST failures and things like that. And essentially, do I have? Yeah, so in this case, you'd have two components. They both cover the same size of the file. And you know, in the initial implementation, you'd create, you know, this one file, and then an asynchronous tool will resync, you know, to a separate copy of the file. And so that would give you, you know, redundancy within, you know, 5 minutes or an hour or whatever, when it'd be probably driven by Robinhood to, you know, get change log record saying, oh, this file is out of date and it needs to be resynced. And so that is a relatively straightforward implementation. It's essentially read mostly copies of the file. And then phase 2, I mean, we've done designs for these things already. Phase 2 is essentially when the client can do the replication and it can write to both copies immediately, right? And then you'd have live data redundancy and robustness against OST failure, even, you know, while you're writing the file. I think that's the last one. Yep. Questions?
We don't have time for a lot of questions, so maybe one.
I'm talking about the data on MDT feature. You said you fixed the layout at open time for the small times. At this time, the file size isn't known yet. So yeah. How do you handle the case when a file slowly gets larger and larger?
So the way that that's going to be handled, the problem again is exactly because we don't know when Lustre determines the file layout when the file's opened, right? And so we don't know the size either, and that's hard to pick. So what I think the initial implementation would target is you just have to specify on your directory, you know, I expect lots of small files to be here. And then if it's writing to the MDT, or if it immediately starts to write and is larger than the 1 megabyte or 64K or whatever threshold, the client will just transparently, you know, talk to the MDT, change the layout to be an OST-based layout, and then write the data. I mean, if you're writing only 64K twice, that's not a huge deal, right? And in fact, these files may grow very quickly and not even be flushed to the MDT. But yeah, that needs some further thought. But
okay, but you don't intend to have the very first part of the file on the MDT and the rest on the OST?
No, it would take up way too much space on the MDT, right? If you had 1 megabyte or whatever of every file on the MDT, it would be way too big.
I'm sorry, we are a little bit late already in the schedule, so you can ask this question to Andreas at the break. Thank you, Andreas.